Hi everybody, the purpose of this video is to go over the last section in chapter 6. Yes, that is section 6. Section 6, try to say that 3 times fast. And here we are going to talk about the graphs of the secant and cosecant functions. So as you might expect, in this video we're going to talk about, yeah, you guessed it, the graph of the secant functions. Then we're going to talk about the graph of the cosecant functions. Then we're going to talk about some techniques for graphing secant functions, or more importantly for recognizing the correct graph, which is what you'll have to do in your homework. And then finally we are going to take a graph and then determine the correct equation for that graph. And yes, that equation will have either a secant function in it or a cosecant function in it. Okay, so this right here is the plot for a secant function. Now remember, the secant is the reciprocal of the cosine. So whenever the cosine is equal to 0, which of course are at the odd multiples of pi, secant will be undefined. However, whenever cosine is equal to either 1 or negative 1, which will occur at all integer multiples of pi, then so secant and cosecant will take on the exact same values. So actually with that, we can actually plot some points and figure out what the graphs are. Of course, to plot one period of a secant function, it's probably best to start at negative pi over 2 and go one period over. So let's do that. Starting at negative pi over 2, cosine is 0, therefore secant must be undefined. At negative pi over 4, cosine is equal to 1 over the square root of 2. So secant is equal to the square root of 2. At x equals 0, both cosine and secant take on the exact same value, 1. We go back up to the square root of 2 of pi over 4, and as we approach pi over 2, we are undefined again. Once we cross pi over 2, secant becomes negative. And as we approach 3 pi over 4, since cosine is negative 1 over the square root of 2, secant is negative root 2. Once again, at pi, secant and cosine have the exact same value. And of course, when we reach 5 pi over 4, secant is equal to negative root 2, and then it goes all the way down and becomes undefined. And notice that secant is happy over here. It's a happy smile. And over here it is sad. So one of the reasons why I say these functions are bipolar. That's my pathetic attempt at math humor. Here is a comparison between secant and cosine. Once again, when cosine crosses the x-axis, secant becomes undefined, and of course when cosine is either equal to 1 or minus 1 at the multiples of pi, well then secant takes on the exact same values. As a matter of fact, we can use cosine as a tool for drawing the secant function. So what do we want to say about these? Well, once again, the graph is undefined and has vertical asymptotes at all odd multiples of pi. And once again, this is a mathy way of saying odd multiples of pi. Also notice that we have vertical asymptotes at every half period. That comes in handy for actually plotting points. And also notice that the graph has no x-intercepts. It never crosses the x-axis. And since the graph has no maximum and no minimum, it has no amplitude. And also, as you can see right here, the graph is symmetric about the x-axis, just like the cosine function. And therefore, secant is an even function, just like the cosine function, and satisfies this equation for every single value of x. Next is the cosecant function. Notice the cosecant function is the reciprocal of the sine function. Therefore, whenever sine is equal to 0, which is at every integer multiple of pi, cosecant is undefined. Whenever sine is equal to 1 or negative 1, which occurs at all odd multiples of pi over 2, then cosecant and sine have the exact same value. And so with that, we can actually go ahead and walk through some points and plot this. When x is, and to plot this, of course, we are going to start for one period. We are going to start when x is equal to 0 and go all the way up to 2 pi. So when x is equal to 0, sine is 0, so cosecant is undefined. As we increase to pi over 4, cosecant becomes the square root of 2. As we increase to pi over 2, cosecant becomes 1, the same value as sine. As we continue on to 3 pi over 4, cosecant is root 2. And as we continue on to pi, sine becomes 0, therefore cosecant becomes undefined. As we cross pi, we go into the negative range. and as we increase up to 5 pi over 4, cosecant becomes negative root 2. It then reaches the sine value at 3 pi over 2, which will be negative 1, goes back to negative root 2, and then as we continue on to 2 pi, it goes all the way up to, or becomes undefined. This is a comparison with cosecant and sine. Again, once again, whenever sine has an x-intercept, cosecant has a vertical asymptote. Whenever sine reaches a maximum or a minimum, the cosecant reaches the exact same value. So at all odd multiples of pi over 2, cosecant and sine have the exact same value. And what can we say about the cosecant? Pretty much similar to what we said about secant. It is undefined and has vertical asymptotes, 3 asymptotes per period. And notice that in this case, however, they occur at all multiples of pi. However, they do occur every half period. It has no intercepts, just like secant, and it also has no amplitude. The other primary difference between the two, and you can't really see it in this graph, but you can see it here, is that the cosecant, just like the sine function, is an odd function, and therefore satisfies this equation for every single value of x. So that is everything that we want to talk about relative to the secant and cosecant functions. But now we need to talk about how to either plot those functions for the most general form, which is right here, with the exception of the vertical shift. I forgot about that. Or at least recognize the correct plot. Okay, and this is a 4-step approach in which to do that. The first one is to graph the corresponding reciprocal function. Why? Because that function would be a useful tool in graphing the corresponding secant or cosecant function. Just as an example, once again, if you've graphed the sine function, if you graph the sine function as a tool for graphing the cosecant function, at these points they take on the exact same values. Whenever sine crosses 0, that's where your asymptotes are. So you could actually use this to draw that. So the idea here is to use cosine or sine as a tool for graphing secant and cosecant respectively. Once you've done that, you need to sketch the vertical asymptotes. Now, if you did not use this approach, what you're going to need to do is solve these 3 equations. This will give you the leftmost asymptote for one period, this will give you the center asymptote for one period, and this will give you the rightmost asymptote for one period, as will these for the cosecant functions. Okay, and once you have found and sketched those asymptotes, the next thing you want to do is find the midpoints. Okay, and these midpoints will be x1 and x2. You want to find those midpoints and compute the corresponding values. What you'll notice is that when at x1 and at x2, the secant function, the secant function will produce the exact same value as the cosine function, and the cosecant function will produce the exact same value as the sine function. Once you've done that, you want to determine which value is the larger value and which value is the lower value. That is only an issue if you actually have a vertical shift and one is above, and if they're both above or below the x-axis. The thing is the midpoint that has the higher y value is going to have a U shape that opens up. The midpoint that has a lower y value will have a U shape that opens down as they approach the corresponding asymptotes. And that's pretty much it. Okay, so let's see how this works in an example. Okay, here we want to graph, or at least in our homework, we want to recognize the correct graph for the equation y is equal to 3 times secant of 2x. Well, there's a few things we can understand right away. This does not have the appropriate shape for a secant function. So this graph is out. This graph also does not have the appropriate shape for a secant function. This is actually a cotangent function. This graph is out. So it's between these two graphs. So the first thing we want to do is compute the period. And you'll notice that we actually, in your notes, I actually have an entry where you can compute the period. And the period will be equal to 2 pi divided by b, which in this case is 2, and that will give us pi. Okay? Now we want to compute the 3 vertical asymptotes. Now I'm going to call the first vertical asymptote xv1. And what we're going to compute to figure out what that value, to figure out what that vertical line is, I'm going to set 2 xv1 equal to negative pi over 2. And of course that will give me that xv1 is equal to negative pi over 4. I'm going to compute the second one by setting 2xv2 to positive pi over 2. And of course if I solve that, I am going to have that xv2 is equal to pi over 4. Now notice, the difference between these 2 points is pi over 2, which is half of a period. Which kind of makes sense because we just got through saying, and we just got through discussing how all the vertical asymptotes occur at every half period. And since the period here is pi, the half period is pi over 2, so it's working out just fine. As a consequence, we can deduce, without having to solve the equation, although solving the equation is not really all that challenging, that xv3 is going to be pi over 4 plus pi over 2, which would give me 3 pi over 4. So those are our 3 asymptotes. We would have xv1 equal to negative pi over 4, which actually is this one and this one. xv2 is pi over 4, which is this one and this one. And xv3 is 3 pi over 4, which is this one and this one. So this doesn't really do us any good. So we need to look at the midpoints. Now remember, the first midpoint, I'm going to call it x1, is halfway between negative pi over 4 and positive pi over 4. So x1 is equal to 0. So if x1 is equal to 0, we need to evaluate we need to evaluate y when x1 is equal to 0, and that's going to give us that y1 is equal to 3 times the secant of 2 times 0, or 0, which will give us 3. So that gives us 1.0, 3, and that actually is everything we need to make a decision. At 0, we're at negative 3, so this can't be it. This right here must be the graph. But let's go ahead and take a look at x2. Now x2 is going to be between pi over 4 and 3 pi over 4. And the midpoint between those 2 points is going to be pi over 2. So x2 is equal to pi over 2. Therefore y2 is going to be equal to 3 times the secant of 2 times pi over 2, which will be 3 secant pi. Secant of pi is negative 1. This is going to be equal to negative 3. So our second point is going to be pi over 2, negative 3, which of course is this point right here, which reinforces that this is the correct graph. So that's the idea behind determining the appropriate graph, which basically is the majority of your homework. Find your asymptotes, take a look at these 2 points, and then you will have everything that you need to deduce the correct graph. Let's go on to an example 2. This is a cosecant function with a phase shift. And once again, we want to find the correct graph. Well, we can eliminate 2 right away because this is a sine function. Okay, so this is gone. This right here is a cosine function that's been reflected across the x-axis. So this can't be one of them either. So it has to be one of these 2. Of course, to figure this out, once again, we need to compute the asymptotes. Now the equation for the leftmost asymptote is xv1, once again the argument, which is xv1 plus pi over 4, that must be equal to 0. Therefore, xv1 must be equal to negative pi over 4. Now there was something that I forgot to do. What is that? I forgot to compute the period. Okay, well the period is going to be 2 pi divided by b. Well, b is basically implied to be 1 here, so our period is 2 pi. And our half period is pi. So, like I mentioned before, This is the leftmost vertical asymptote. All the other vertical asymptotes are going to be 1/2 of a period away, or basically a distance of pi away. So if xv1 is at negative pi over 4, then xv2 is going to be at negative pi over 4 plus pi, which would give you 3 pi over 4. Which of course is this line right here, or this line right here. So we have that xv2 is equal to 3 pi over 4. And of course we can use xv2 and 1/2 of a period to figure out what xv3 is. I'm going to do that up here where it's safer. We will have xv3 is equal to xv2, which is 3 pi over 4, plus pi, and that will give us 7 pi over 4. So xv3 is 7 pi over 4, and xv1 is equal to pi over 4. Negative pi over 4, I apologize. Pi over 4. Okay, got a little cramp there. Okay, cool. So those are our 3 asymptotes. Unfortunately, these are the exact same asymptotes, so that's not going to do us any good, so we need to figure out the midpoints. Well, the first midpoint, I'm going to call x1, is going to be halfway between xv1 and xv2. And if you computed that, that will be pi over 4. x2 is going to be the midpoint between xv2 and xv1, and that will be 5 pi over 4. Okay, well, y1 is going to be equal to 3/2 cosecant of x1 plus pi over 4. That is going to be 3/2 cosecant of pi over 2, which will be 3/2. Okay, and then y2 is going to be 3/2 times the cosecant of 5 pi over 4 plus pi over 4, which will be 6 pi over 4, which is the same thing as 3/2 cosecant of 3 pi over 2, which of course is -1. Multiply that by 3/2, you have -3/2. So we have 2 points here. The first point is for x1, pi over 4, comma 3/2, which by the way is this point right here. And then the other one is 5 pi over 4, -3/2, which is this point right here marked with an A, which was basically a mistake. Notice here I have pi over 4 -3/2, so this can't work, and neither can that, so this must be the graph. So once again, by computing your asymptotes, then the midpoints, you compute everything that you need to figure out the correct graph. And this brings us to our last set of examples, which is to determine the equation for the following graph. So let's take a look at this graph right here. If you'll notice, it is even about the x-axis. I'm sorry, it is even about the y-axis. So what in the world does that tell us? Well, that tells us this is a secant function of some sort. This is a secant function. Okay? Now, a secant function normally has asymptotes at negative pi over 2 and positive pi over 2. However, these have asymptotes of negative pi and pi. So what you can see is that we actually have a horizontal stretching going on. And if there is a horizontal stretching, we have secant is equal, we have the secant of 1/2 times x. There's actually another way that you can look at this. Okay, we know for a fact that the argument bxv1, because this is kind of like this is xv1, the first vertical asymptote, that is going to be equal to negative pi over 2. Okay, well here we're at negative pi. Okay, so if I substitute negative pi for v1, I'm going to have b times negative pi is equal to negative pi over 2. This cancels, and I'm left with b is equal to positive 1/2. And so that gives me that y is equal to the secant of 1/2 times x. Is there any vertical scaling going on here? No, because when x is equal to 0, secant is equal to 1, so there's no vertical scaling. And also, when x is equal to 2 pi, we have negative 1 and negative 1 here. So it turns out that this right here is our answer. Okay, what about this one? Well, notice the first thing that we can notice is that we have an odd function. Since we do have an odd function, we are thinking, and we also have a vertical asymptote at x equals to 0, we actually have a cosecant function. Okay, now also notice that the cosecant function basically has a period of 2 pi. This is the negative part, which is pi. This is the positive part, that is 2 pi. Okay, and since the basic cosecant function has a period of 2 pi, we know that this should be cosecant x. Now notice here that we are at 0 at this point and negative 2 at this point. It's almost like we took this curve like this and shifted it down by 1, which is actually what we did. We have a vertical shift. So this right here is our vertical shift of negative 1, and this is our answer. So that's pretty much how you would deduce the correct function, or the correct equation for this particular graph. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.